to this point in our discussion, matrices have just been ways of writing down arrays of numbers. However, the real power of matrices comes from their algebra. Since matrices are a very economical way to write down the linear algebra that we encounter so often in science and engineering, their algebra is particularly important because of the simplification and the generality that it brings. Quantum mechanics in particular turns out to be based completely on linear algebra, as we already said. To be able to use matrices as a very convenient way of writing down and working with linear algebra, we need to define their various algebraic properties. Now, the algebra of matrices has many similarities to the algebra of ordinary numbers and variables, but it does have some very important and consequential differences. And these differences give a richness to the algebra that makes it particularly useful for describing linear physical systems. We are going to look at the basic processes here, showing how those processes with matrices are similar to and different from our ordinary algebra. We will start with addition and subtraction, and then move on to the particularly important process of matrix multiplication. And that is where matrices start to get their real power. We will end by discussing the inverse of a matrix briefly.
Now let's look at the simplest perhaps of the matrix operations, adding and subtracting matrices. If two matrices are the same size, that is, if they have the same numbers of rows and columns, we can add or subtract them simply by adding or subtracting the individual matrix elements. And we do this one by one on each of the elements. So for example, if we have a matrix here like F, 1 and I, 2 and 1 minus 3i as its elements, and similarly another matrix G with its corresponding elements, then to add the two of these together to get a new matrix K, we simply add the elements in each matrix one by one. So 1 plus 5 gives us our new element for K, I plus 4i here, 2 minus 6 here, and 1 minus 3i plus 7 plus 8i. And of course we can simplify that to get the result. So that's very straightforward. Now let's look at a somewhat more complicated but very important operation that we can do with matrices, which is multiplication. And we're going to start that discussion by taking a particular case, a simpler case, which is multiplying a vector by a matrix. So suppose we want to multiply this column vector here by a matrix. The number of rows in the vector, you will see here, must match the number of columns in the matrix. And this is a general requirement for matrix-matrix multiplication, is this matching of the rows in one with the columns in the other. So you can see that the number of rows on the right, which is 3, matches the number of columns on the left in the matrix here, which is also 3. So how do we do this? Well, the first thing we do is we imagine that we take this vector and put it sideways on top of the matrix. And then we multiply element by element. So we have 7 times 1, which we have here, 8 times 2, which we have here, 9 times 3, which we have here, and we add all of these up, and the result of that is 50. And that's the number we put in here. And this result here is going to be a vector, and the first element in the vector, this top one here, is the result of the product of this vector with that matrix. So we can keep going here. We can move down and repeat for the next row. We move our 7, 8, and 9 down to multiply them. 7 times 4, 8 times 5, 9 times 6. And we have all of these here. We add them up and get 122. And notice that we put this in the lower element of this vector. So we have two rows in this vector which matches the two rows in the matrix. So here's our result, just in shorter form, the 50 and the 122 here as the result of multiplying this vector by this matrix. And we can also write this in an algebraic form if we think of this result vector here as being vector D, and our input vector here on the right as being vector C, and our matrix as being matrix A. We can write D is equal to A times C, of course. And we can also write this out in a summation notation. So the dm here are the elements of this vector, so there's two of them, so m runs 1 and 2. The cn here are the elements of this vector, 1, 2, and 3. And you see what we're doing here, we're summing over n, cn times amn. So for the first row, the m is going to be 1. So we're multiplying the elements in the first row, m equals 1, by their corresponding elements in the vector, amn times cn. So this is am1, am2, am3. And note that the summation in this notation is over the repeated index. So we've chosen to sum over n here, but we see that that is also a repeated index in the sum. So this expression here is just the same as the operations that we've just done. Now we can keep going here to the more general case of multiplying a matrix by a matrix. So here is a matrix and another matrix, and we're multiplying this one by this one, and here is our result. The first column in this matrix here is the same as the vector we were just working with. This matrix is the same as the matrix we just worked with. So these first two elements here on the left column are indeed the ones we just worked out. This one here, the 14, is the result of taking this vector 1, 2, 3, laying it across the top, doing 1 times 1 plus 2 times 2 plus 3 times 3, and that gives you 14. And similarly, the 32 is 1 times 4 plus 2 times 5 plus 3 times 6. So you see that the results in this first column here are the ones that we get from the first column of this matrix on the right, and the ones in the second column are the ones that we get from the second column in the matrix on the right. So as we've just done, we see that what we do is we repeat our operation for each column in the matrix on the right, working from left to right to work from left to right in the result. And we write down the answers as the elements in this matrix here, also working from left to right. Again, we can write this algebraically. Here is our result matrix equal to matrix B multiplying matrix A. We call this matrix A, this is matrix B. And in summation notation, we get something exactly analogous to what we just got for the matrix vector multiplication. We're looking here at the mth element of this matrix. So for example, for m equals 1 and p equals 1, that's this element here. And we are collecting for each column here. We choose a specific column, column P, for example. You see, we're doing the same thing as we did for our vector matrix multiplication, and we're summing over the repeated index n in the middle. So the elements with p equals 1 are just this column of numbers here, and we're doing the same thing as we did before to generate this element, and so on. A particular special case of matrix-matrix multiplication is the rather simple one of vector-vector products. And we're going to work with these to point out some of the things that happen when you take vector-vector products, which turn out to be quite interesting. If we take two vectors like this, a column vector on the right and a row vector on the left, then we see doing our matrix vector multiplication here, with this as our matrix, we're going to do 4 times 1 plus 5 times 2 plus 6 times 3. But the net result of that is just one number. So this particular vector product of a column vector on the right and a row vector on the left collapses everything to just one number. And this is sometimes called an inner product. And it's completely analogous to the geometrical vector product. In fact, this could actually be a geometrical vector product. If 4, 5, and 6 were the components in the x, y, and z directions of an actual geometrical vector, and 1, 2, and 3 were the components in the x, y, and z directions of another geometrical vector, then this result here would in fact be the dot product of these two geometrical vectors. The algebra is actually the same. Again, we can do this algebraically. We can have this number here, f, equal to a vector, in this case a row vector, and a column vector multiplied together. Note that here we are running into a slight notation problem in that I'm using ordinary letters both for numbers and for vectors. Later on we'll get to a different notation called the Dirac notation that gets past that particular confusion. And then again we can write this in summation form here, which turns out to be particularly simple. We again are summing over the repeated index, and the result here is just this one number. In contrast, if we multiply the vectors the other way around, so we put the row vector over here and the column vector here, then when we multiply the two of these together in this order, we actually generate a complete matrix here. And in this matrix, 1 times 4 gives us this 4 here, 2 times 4 gives us this 8 here, 3 times 4 gives us this 12 here, and so on. And this product is sometimes called an outer product, with the two vectors combining in such a way as to give us this entire matrix. It's kind of the opposite of what happened with the inner product, where they combined to give us just one number down here. And again, we can write this out in algebraic form. So now we're forming a new matrix, F here, and it's a product of the column vector D and the row vector C. Again, this notation is a little insufficient because it's not making it clear whether either of these is a row or column vector, but we know they are from here. And the net result of that is that the mth element of this matrix is the product of the mth element of the column matrix times the pth element of the row matrix. Matrix algebra has many similar properties to the algebra of ordinary numbers, and one very important difference. So, first of all, matrix algebra, like normal algebra, is associative. So it does not matter where I put the parentheses here, whether I put them around the C and the B or around the B and the A. That is, I could multiply C and B together and then have them multiply A, or I could multiply B and A together and then multiply C by that result. It does not matter which one of these we do. It also has the same kind of distributive properties that we're used to from normal algebra. So A times the sum of B plus C is equal to AB plus AC. But matrix algebra is not, in general, commutative. That is, in general, it's not the case that if we take two matrices A and B, that the product B times A is equal to the product A times B. Now, it is possible that for some matrices this may be true, but it's not true in general. And this is easily proved with a simple example. For example, if we take these two matrices here and multiply them together in this order, we'll get the following result. But if we take the same matrices but multiplied in the other order, so this one is now here and that one is now here, then the answer is simply different. So we are proving by example that in general B times A is not equal to A times B.
Whether or not any two specific matrices commute, that is, whether A times B is the same thing as B times A, turns out to have some major mathematical consequences for the two matrices and their shared properties. The fact that matrix multiplication is not in general commutative is extremely important in allowing matrices to be at the core of the way we describe quantum mechanics, and it has profound consequences in the physics. The fact that some specific matrices do commute with one another, that is, we can swap the order of multiplication, also has very specific consequences in the physics. We're going to return to these topics in our discussion of quantum mechanics.
Multiplying a matrix by a number turns out to be very straightforward. It means basically that we must multiply every element of the matrix by that number. So for example, the number 2 multiplying this matrix here simply means we go in and multiply each element of the matrix by the number 2. Also, similarly, we can do the opposite. We can take a common factor out from every element, in the end multiplying the matrix by that factor instead. So if we had started out with what was this matrix here, if we start out with this matrix, we can rather obviously take out the factor 2 from all of these elements and put it out the front. And if we want to do a formal proof, we use the summation notation. In fact, that's generally true. If we really want to prove things for matrices, we tend to write them out algebraically using the summation notation if we want to get a very clear result. So for example, we can show how to do a proof for this idea that we can separate out this factor from the matrix, or we can introduce it one way or the other. We presume that we're going to take this matrix A here and have it multiply an arbitrary vector, and we're going to look at the vector we get as a result. And that's a way of proving things for some matrix or operator here. To prove equalities of one kind or another, we can prove them by having them operate, the matrix here operate on an arbitrary vector, and show that it works for any arbitrary vector. So here, for example, we've got our matrix A multiplying the vector C, and we're multiplying the whole thing by some number alpha, and the result of that is some vector. Now, because these entities here are all just numbers, we can move this alpha in here, put it inside the summation. That's a normal operation with numbers. A times the sum of a bunch of numbers is the same as the sum of A times each number. That's really a distributive property. And consequently, we can move this alpha here formally inside the sum. And then if we want, we can put parentheses around this pair of terms inside the sum. And this here is just a number that we can call a matrix element of another matrix, Bmn. So this is a rather trivial proof, but I formally proved that you can take this alpha that was outside the matrix and instead multiply every element of the matrix. So I've essentially proved that this works. It's a very trivial proof, but it shows the kind of way that we can prove things using summation notation. So formally, this matrix element Bmn is alpha times the matrix element Amn. Now, in multiplying a matrix by a number, we know, of course, that number multiplication is commutative. So if we have some product of numbers and matrices, we can simply move factors around arbitrarily in matrix products. So for example, if we've got a number alpha and a vector c, then alpha times A, the matrix A, times the matrix B times the vector c, means we can move this round. We can move the alpha round inside here. Since it was just multiplying every element of this, we can also take that out and put it on the other side, and so on. And we can keep on moving the numbers around inside here as much as we want. So alpha times A times B times C is the same thing as A times B times alpha times C. But notice we've not moved the order of the matrices around, but we can move numbers around. And again, if we want to formally prove something like this, it's pretty straightforward to do so using the summation notation. Now, something that comes up quite a lot in the algebra of matrices and linear operators generally is we often have to take the Hermitian adjoint of a product of two matrices. And the Hermitian adjoint of a product turns out to be the reversed product of the Hermitian adjoints. So if we had a product of two matrices here, A and B, and we wanted to take the Hermitian adjoint of that product, then it turns out that it's equal to the product of the Hermitian adjoint of B times the Hermitian adjoint of A. And again, this is something that we can prove using summation notation. So let's just do this as an exercise using the summation notation. Let's suppose that the matrix R is the product of the matrices A and B in this order, so that the matrix element RMP is the sum over n of the product of the mnth element of A times the npth element of B. So, if we look at the pm element of this Hermitian adjoint of this product here, by definition here, it must be the pm element of this matrix R adjoint, R Hermitian adjoint. And the pm element of R Hermitian adjoint is the complex conjugate of the mpth element. And that's the definition of taking the Hermitian adjoint. So, therefore, the pmth element of this matrix must be the mpth element of R complex conjugate of that element. And that, of course, is just amn bnp summed over n and complex conjugated, which we can rewrite like this, because the complex conjugate of a product is the product of the complex conjugates. But this element here, A star mn, would be the nmth element of the matrix A dagger, A Hermitian adjoint. And similarly, the complex conjugate of the nth element of B would be the pnth element of the Hermitian adjoint of B. These are just numbers, so we can swap them round. And of course, this is just the matrix product of B dagger times A dagger, as we have here, the pmth element of that. So we've shown that the pmth element of this matrix is the same as the pmth element of that matrix. So therefore, because this is true for any choice of P and M in the matrix, we have proved our result up here.
One final topic in matrix algebra here is the inverse of a matrix. In normal algebra, as well as addition and subtraction and multiplication, we have division. In matrix algebra, though, there is no operation of division as such. We do have a concept, however, that can perform some of the functions of division, which is taking the inverse of a matrix. With numbers, the closest analogy is the reciprocal, which is 1 over a number. 1 over some number is the reciprocal. We know that for the number 0, there is no meaningful reciprocal. 1 over 0 is not defined. But otherwise, division and reciprocals are meaningful and useful for numbers. Now, many matrices do have an inverse, but there are also many matrices that do not. The conditions under which matrices do or do not have inverses are quite an important part of the mathematics of matrices, and we will also be returning to this later.
So let's look at the inverse of a matrix and what specifically we mean by that algebraically. For ordinary algebra, the reciprocal or inverse of a number or variable x is simply 1 over x, or we might write that as x to the minus 1. Now, it's not clear what we would mean by 1 over a matrix, so we can't use that notation. However, we will try to make some use of a notation like this. Anyway, for ordinary numbers, this quantity x to the minus 1 times x is the same thing as x over x, and it equals 1. For a matrix then, what we say is the following. If a matrix does have an inverse, we'll write that as a to the minus 1. It will have the property, and this is really a definition of our inverse here, that a to the minus 1 times a will equal the identity matrix. So whereas x to the minus 1 times x equaled the number 1, for the matrices we're writing something similar, that a to the minus 1, if it exists, times a is equal to this idea or concept that we call the identity matrix. And the identity matrix is the diagonal matrix. That is, a matrix with only elements down its diagonal and 0 everywhere else. And in the case of the identity matrix, the elements on the diagonal are all 1. So the identity matrix has 1s down its diagonal and 0s everywhere else. For example, the 3 by 3 identity matrix would look like this here. 1s down the diagonal and 0s everywhere else. Now, when we're doing a multiplication with the identity matrix, the multiplication will not make any sense unless we've chosen the identity matrix to be the right size. So we don't even need to bother saying how large the identity matrix is, because it obviously has to be the one that's the right size so we can do the multiplication. So we do not usually bother to be explicit about what the size of the identity matrix is. But obviously there are lots of different identity matrices depending on what dimension or what size of matrix we're talking about. For any matrix A, we can write A times I here is equal to A, or we can write I times A is equal to A. This is really the definition of the identity matrix. Like the number 1 in ordinary algebra, it seems on the face of it perhaps that the identity matrix is almost a trivial idea, but in fact it's very important. And just as the number 1 is very important in ordinary algebra, so also the identity matrix is very important in matrix algebra.